Here are our follow-up on sequences. If you were not in class when we discussed geometric sequences, or if you are struggling, that is what we're going to focus on. So we already looked at arithmetic sequences, and we said they always have a common difference. You're always adding or subtracting the same amount, plus 2, plus 2, plus 2. The biggest difference between geometric and arithmetic is we're talking about a common ratio. Okay, so instead of adding or subtracting the same amount and calling that your D value, we're always going to be multiplying or dividing by the same amount, and it will be your R value instead, okay? It's that multiplicative rate of change that we discussed when we were doing exponential problems and functions and graphs. So a really good example would be if I have this sequence, 2, 6, 18, 54, 162, and so on. So you notice it's not additive because we add 4, then we add 12, then we add a lot more than that. So there's definitely not a common difference. But the common ratio, well, 6 over 2 for a ratio would be I'm multiplying by 3. 18 over 6 shows that I'm also multiplying by 3. I'm multiplying by 3 to get to 54, and I'm multiplying by 3 to get to 162. Okay, so that is telling me that this is definitely geometric. It has a common ratio of multiplying by 3 every single time. Okay, now just as a quick reminder about sequences, our tables on these, usually when we build a table, we like to see that y-intercept value, that 0 value. But it's very important to remember, sequences do not start with the y-intercept. That's what makes them so different from all the other relationships we focused on this year, is we're actually starting with the first term, then the second term, then the third term, then the fourth term. So if I was to look at it at a table, like how we've typically seen relationships, that 2 is not the y-intercept value, it's actually the first value, then the 6, the 18, and the 54 all the way down. So if I want to know the y-intercept value, because remember if I'm writing exponential formulas, it's a number times a number raised to an exponent of x. Okay, that's previous notes that we took that you can find. So this front number is my y-intercept, it's where am I starting, my initial value. Not the 2, because the 2 is the first value. So I would have to figure out, okay, to back up and get a number that when I multiply by 3, it equals 2. So I need something times 3 that equals 2. It's not going to be clean. The shortcut is to say, oh, well, I'm going to divide by 3 to back up. So 2 divided by 3 is just 2 over 3. It's 2/3. If you do this on the calculator with the actual control enter to get the decimal, you'll get a repeating 0.6. So my y-intercept, if I do the math on that, is 2/3. Every time I am multiplying by 3, that would be my growth rate. This is tripling every time we're tripling, raised to the x, because we don't know how many 3's we're multiplying by. We're just multiplying by a lot of 3's. So if I go to the sequence formula, remember, basically it's a simple shift. Okay, I change y to a sub n. It's still the same basic formula. The only difference is instead of an x, we use n. So remember we did that on arithmetic. We said, oh, so it's the same numbers. It's just instead of an x, you put an n. Well, kind of similar to your arithmetic, if I don't want to figure out that y-intercept, if I want to write my formula and say, no, you know what? To me, this sequence starts at 2. So I'm going to say I start at 2. And then I'm multiplying by a bunch of 3's. Times 3 times 3 times 3. Well, just like in arithmetic, if I take the first term, then I'm going to have an n minus 1 to kind of say, hey, my term that I'm on, I've got to take away that shortcut I got at the beginning. So there are our two formulas. Very similar to what we did with arithmetic sequences, but it's just instead of using an mx plus b format, I'm using the exponential format. Instead of linear, we're going exponential. So I can either write it a to the 0, or a sub 0 times the common ratio raised to the n. So I can start with the y-intercept, which is the 0 term. And then that r represents the common ratio. So what are we multiplying by every single time? Raised to a normal n. Because I did the math, I backed up to get the normal y-intercept that we typically focus on. Or the other option is to say, you know what, I'm going to start with a sub 1. I'm going to start with that first term because that's really where my sequence starts. It's still times r raised to the n minus 1. Okay, so you have two options. It's your option which one you use, but you do have to be very careful about, did you back up to where the y-intercept should be? Then you use a plain old n, or am I just starting with the first value? In that case, you have to do n minus 1 to say, ah, yeah, I'm not starting at the 0 value. I'm starting 1 ahead, basically. And then it's still using your common ratio. So I want to give you a couple of examples to kind of practice writing these formulas and also to practice evaluating specific values. So these are the examples I did over arithmetic. I'm just going to add on to that page. If we go 20, 10, 5, 2.5, ... The first question is it geometric or arithmetic? We now have two options. We've seen two different versions of these sequences. Well, let's see what our pattern is. Subtracting 10, subtracting 5. It's not arithmetic. Dividing by 2, dividing by 2, dividing by 2. Every single time I'm cutting in half, that makes this thing geometric. So instead of discussing the d value, the common difference value, I'm going to figure out the r value. What am I multiplying by every time to change to the next number? I know it's very natural to say dividing by 2, but we want to think about this as a multiplication. So instead of dividing by 2, I can multiply by 1/2. Okay, so you could say 0.5, or you could say times 1/2. You need to know at this stage that dividing by 2 can also be written as multiplying by 1/2. Okay, don't think of it as division. Figure out how to write it as a multiplication problem. So I have two options. The first one, if I back up to the y-intercept, because again, this is the first term, I have to back up to the 0 term. So, okay, if I'm going to follow this pattern kind of going back the other direction, I'm going to actually multiply by 2 or divide by 1/2, which gets really confusing. But sometimes it helps to just put a number down and then go, okay, 40, 20, 10. That follows my pattern. So I can start with 40. My common ratio is 1/2 because every time I'm multiplying by 1/2 to the n. I went all the way back to the y-intercept, so I don't have to do anything fancy with my n. Or I can take the shortcut and say, nope, let's start where the sequence starts, 20. My common ratio doesn't change. I'm still multiplying by 1/2, just the same as I was when I backed up one stop. But I just have to make sure to put n minus 1 to make up for that shortcut we just took. Okay? If I ask you to find a value like a of 6, all that's asking you to do is say, hey, find the 6th number in the list. And I want us to move away from saying, oh, cut it in half, cut it in half, cut it in half, cut it in half a couple more times to get there. I want to actually use this formula. So like if I use the top one, I would actually do 40 times 1/2 raised to the 6th. I'd put that in my calculator, type it in exactly as it appears, just the back part that I need to work out, and it would tell me that a sub 6 is 0.625. Or it might tell you that it's 5/8, depending on how you type it in your calculator, okay? So, one more example real quick, kind of a nasty one. If I go from 4 to 8/3 to 16/9 to 32/27, let's figure out what that pattern is. And I encourage you to pause it and try and come up with the pattern on your own. I'll kind of give you a second to do that. It's not adding or subtracting the same amount. I can do that on a calculator. I can do some simple subtraction and see that that is not a consistent addition or subtraction. So it is geometric. And then what kids figured out in class is, hey, the top is always multiplying by 2. The bottom seems to be multiplying by 3 every time. So that actually tells me if the top is multiplying by 2 and the bottom is multiplying by 3, that's my pattern right there. Even the first one, if you make it 4 over 1, 4 times 2, 1 times 3. Okay? Not anything too horrible there. So your 2 formulas would be, if I backed up to the 0 value, to the y-intercept. All right, instead of multiplying by 2, I'm going to divide by 2, which would make this 2 over, instead of multiplying by 3, I'm going to divide by 3. So 1 divided by 3 is 1/3. Guys, that's a disgusting number. 2 divided by 1/3, 2 over 1/3. We don't like fractions within fractions. You can put in the calculator if you want. You can do 4 divided by 2/3 instead of 4 times 2/3. But basically, how many thirds fit into 2 whole? It's 6. So my y-intercept is 6 times my common ratio, which is 2/3, raised to the n. This is why we learned the second version, because that was gross to come up with. So the other way is, let's start with my sequence starts at 4. That's my first term. And then the common ratio and n minus 1. So both of those formulas are perfectly okay. I would argue that that one's a heck of a lot easier to come up with. But you should be able to hopefully make sure that those two match with a little bit of calculator help. Okay? Good luck on the paper.